let's do a problem using Chapter 7 techniques to solve. And then I think what you'll discover is that the Chapter 8 techniques are a little cleaner to use to solve the problem. So why don't we start with a spring that's coiled up and a mass at rest. And let's say, so the spring is going to push it some distance, right? So this is going to be 0 and minus d, and out here somewhere there's plus d, right? So the spring is going to push it until it gets to x equals 0, and then it's going to let go of it. And then we're going to have a let's have a section here with friction from d to 2d. We'll have a rough section, right, with friction. Everywhere else is frictionless. And let's see, should we have it go up somewhere, or let's just let's have it go up a ramp now. And at some point it stops. And we want to know how high it is on the ramp there. How's that? Oh, did I forget the loop-the-loop in the middle? Okay. Starts compressed at one side, ends up there. So the Chapter 7 technique is we are going to find all the work done. The sum of all the work done on the block has to equal the change in kinetic energy of the block. The sum of all the work done on the block has to equal the change in kinetic energy of the block. So what's doing work on the block? First thing. The spring does work, right? What is it doing? Positive or negative work? Let me do it this way. Okay, what's the next thing that does work on the block? How about gravity? Well, let's wait on gravity. How about normal forces? Yeah, the normal force does no work, right? The work done by the normal force is going to be 0. But so the next thing that happens, so the spring pushes on the block, does work on it. The block slides along, hits a patch where there's friction. So what happens there? Friction force does some work on it, right? By the kinetic friction, positive or negative? Negative, right? The block is sliding one way, the force of friction is the opposite direction. You get negative work done, it's going to slow it down a little bit. And then what happens? It goes up. So the force of gravity is doing work on it, right? It's moving. Now, up until it got to the ramp, the force of gravity and the displacement were perpendicular, so there was no work done by gravity. But now, it's going up a ramp. So the force of gravity is not perpendicular to the displacement. So the force of gravity is doing work on it if it's changing in elevation. So at the end there, we do get work done by gravity. And is it positive or negative? Only on the ramp. It's negative because the block is going up and the force of gravity is down. So we're going to get negative work done. Okay, and that's everything, I think. Anything else you can think of? The spring, the friction force, and the gravitational force. That's it here. Okay, should we put some numbers in there? I don't like making up these problems on the fly. We're going to... Okay, so we've got a spring constant. Let's make it 100. We've got some initial displacement of that spring. How much is it stretched by? How about 2 meters? What else do we need to know? We need to know the mass. Let's make it 0.5 kilogram. And we need to know our kinetic coefficient of friction. How about 0.1? And how about theta is 30 degrees? Or let's make this 5 kilograms just to... Okay, mass is 5 kilograms. All right, are we ready? So what do we get over here for all the work done? Work done by the spring is positive 1/2 kx squared, right? And what is that in this case? It's 50 times 4. 200 joules? Did I get that right? We good with the work done by the spring? 200 joules, did you get that? It's 1/2 kx squared, right? 1/2 times 100 times 2 squared. I think that's 200. Work done by friction. That's going to be negative the friction force times the distance. In this case, it's just d, right? And the friction force is going to be the normal force times mu. Mu times mg times d. So what do we get for that? We get d is 2, and 10, and 0.1, 2, and 5, 10. Negative 10, roughly. If we use 10 for g, 0.1 for mu, they become 1. And then 5 times 2 is 10, so 10 joules about. And then how about the work done by gravity? How do you want to do that? I'll show you two ways. First, let's talk about the block going up the incline, right? So it's going to go a certain distance up the incline. What are we going to call that? How about lowercase d? Right, the hypotenuse will be little d. We're trying to find h, the vertical height. So it's going a distance d up the incline. It's going to be the force of gravity, right, times the distance, times the cosine of the angle between them. The force of gravity is mg. The distance is little d. And the what is that angle? (90 plus 30, right? D is in that direction. mg is in that direction. That's 30. That's 90. So what do we get for that? (100) times the cosine of 120. No, sorry, we don't know d. We've got 50d times the cosine of 120. And the cosine of 120 gives us a negative, right? And we expected the work done by gravity to be negative. So that's where it comes from. 1/2. So negative 25d, that's our answer. Okay, so now there's another way to figure out the work done by gravity. D times the cosine of 30 is what? 50 times cosine 120 gives us negative 43.3. Let me fix that over here. Negative 43.3. Okay, so one other way to look at this. So where was I? This side of the triangle is h, right? The height that it goes up. So the force of gravity, we could have said it travels a distance d at 30-degree angle with the force of gravity down, or we could say it goes straight up a distance h with the force of gravity straight down. What do we get when we do that? H is going to be d sine 30, right? What do we end up with over here is 1/2 d, right? So if we just used our vertical distance and the fact that the force of gravity was going down, the vertical distance was straight up, we get a negative mg times h. We get the same result. Okay, same as if we used going up the incline. We're going to talk more about that next chapter. It doesn't matter which path we take, we get the same work done. That's a special kind of force. It's called the conservative force. You could go up the incline, or you could go horizontal and vertical. It doesn't matter what path you take to get from the starting point to the ending point. The work done by gravity is the same over every path. That's a special force called the conservative force. We'll talk about that more later. Okay, so where are we? We've got our work done by every force. We add them all up. And we say that has to equal the change in kinetic energy. So what do we get? We get a plus 200, a minus 10, a minus 25D, has to equal, what's our change in kinetic energy? Zero, right? It starts at rest and it ends at rest. And so what do we end up with? We end up with 25D is equal to 190. And D is equal to, what is that? Sorry, what? 7.61 meters. Okay, so that's the chapter 7 approach. All the work. You look for all the work done, add up all the work done on the object by all the forces acting on the object, and you set that equal to the change in kinetic energy. You can have springs in there, you can have friction, you can have changes in elevation, right? All of those things we can figure out. We can have some external force, somebody pulling with a string or a rope or just pushing or pulling on something, some other force, any force acting on this thing. We can add up the work done by all the forces, set that equal to the change in kinetic energy. So the chapter 8 approach is going to be a little different.